Our first presenter of this panel is Kassie Morton, I believe. Kassie, if you're here, if you could just give a little thumbs up or something to let me know you're ready.
Hi there.
Oh, excellent. Great. Great. Yeah, so Kassie will be presenting on the Ocean Sewage Alliance Knowledge Hub. And Kassie Morton has been a project manager for TNC's global science team for the past 7 years, with a current focus on aquatic wastewater pollution. She's worked for a diversity of inspiring and progressive companies and organizations making an impact on sustainability issues such as renewable energy, green building, agricultural development for smallholder farmers, and conserving nature. Kassie is an outdoor enthusiast, conservationist, mother, wife, and animal lover. Thank you so much, Kassie, for being here, and take it away.
Thank you so much, Julia. Thanks for having me. Good morning. I'm Kassie Morton. I'm a project manager for the Nature Conservancy, and I'm joining you from Bainbridge Island, Washington today, the traditional home of the Suquamish tribe, or the people of the clear salt water. I'm going to share my screen with you. Let's see. There we go. So TNC is a partner of the Ocean Sewage Alliance, which I'll be representing here today. OSA has 28 amazing partners. The Rich Earth Institute was one of our first resource recovery partners. And a huge thanks again to Julia and her team for inviting us here. As I'm sure most of you know, wastewater pollution is harming our aquatic environments, with up to 80% of wastewater discharged globally being untreated. This impacts everything from coral and seagrass health to food security and the economic stability for those dependent on healthy fisheries and tourism. OSA is a diverse collective of organizations and academics who founded the Alliance in 2021 with the goal of reducing wastewater pollution in our oceans and promoting the exciting solutions that exist, like urine and biosolids recovery. The OSA is led by a very dedicated steering committee and fueled by 5 different working groups. And this is where we synthesize evidence to build our case to support and influence decision makers, to grow our collaborations across sectors, which right now we're actually seeking new partners to join us from commercial fishing and aquaculture industries, the circular economy sector, the tourism and hotel industries, and marina sailing and yachting industries. So if you represent or are involved with any of those sectors and have any interest in becoming involved, I'll drop a link to learn more at the end of my talk. But we'd love to have more folks join us to combat this issue. We also have a Uniting Our Voice working group focused on awareness building and messaging to key audiences. We have a fundraising focused working group. And then I'm here to talk to you today about our Knowledge Hub, which we're really excited to share. We just recently launched this late summer. And our Knowledge Hub working group built the first ever open access platform dedicated to wastewater pollution. And I'm just going to, let's see here, swap over to give you a little tour of this resource. Let's see. Give me one moment. I'm sorry. Maybe I need to get out of here. There we go. And then sharing the resource again. Okay, here we are. So the Ocean Sewage Alliance has a great website in general, but our Knowledge Hub is what we're here to talk about. Larissa Balzer is our one of our great leaders with the Ocean Sewage Alliance, and she has this very very entertaining tutorial video that I encourage you to take a look at on your own. But this is the Knowledge Hub that provides a really great overview about the issue of wastewater pollution, has a section on the solutions, gives an overview of the policy landscape, a little primer on understanding the sanitation industry, and one of my favorites is the library. So This library is broken out into all kinds of different resources, briefs, case studies, courses, and it is searchable by region, or up here for those of you focused, of course, on resource recovery. You can type that in and it will pull up and sort by everything related to urine and biosolids recovery. And there's all kinds of different articles and papers and podcasts. So lots and lots of great resources there, specifically tied to the interests of this group. And then I encourage you to take your own tour. There's just so much to be found in this wonderful collection of, I think there's upwards of 350 different actual pieces of everything. We try to focus on solutions, but also balancing it with a good background of the understanding of what wastewater is doing both in the environment and how it's impacting human health as well. So I'll go ahead and drop a link to the hub in the chat, but I really encourage you again to take a look. And then if you have any interest in collaborating with us, we've also just added this collaboration page to the website where you can subscribe to our newsletter, join our Slack community, apply to become a formal OSA partner as your organization, or to join a working group. There's a little form you can fill out to tell us what you're interested in getting involved with. And yeah, I think that's it. Does anyone have any questions?
Thanks so much, Kassie. So exciting to see all of those resources together. And at the very end of this panel, we'll have another presentation about another place to look for resources. So it's really nice to be able to cross-pollinate in this way. If folks do come up with questions, we'll have time for some at the end of this panel as well. So I'll move right along to our next presentation, which is from Umakanth Badeti, whose presentation is titled Estimation of Energy Consumption, Greenhouse Gas Emissions, and Process Design for Pre-Treatment of Source-Separated Urine at a Decentralized Wastewater Treatment Plant. And Umakanth Badeti is a PhD student at the University of Technology, Sydney, and his research focuses on studying the impact of source separation of urine on a decentralized wastewater treatment plant. So we have received a pre-recorded presentation from him, which I'm going to attempt to share, and hopefully the sharing will go smoother this time than it did yesterday. So hopefully folks are seeing this these slides here.
Hello, familiar with the effect of urine. Hello everyone, my name is Umakanth. I'm a final year PhD student, and I'm very happy to share with you all my research work on impact of urine diversion and conversion to fertilizer products in Sydney Centre Park. Familiar with the effect of urine diversion on nutrient cycle. It closes the loop, reduces chemical fertilizer demand, and also waste and pollution. In this context, particularly, my research interest is to understand how urine diversion has an impact on the wastewater treatment plant. And to pursue this research, we carried out a case study on Sydney Central Park wastewater treatment plant. This treatment plant is located in the basement of Central Park Mall and serves a population of about 6,600. It is an advanced and decentralized wastewater treatment process comprising biological and membrane treatment process like MBR and RO. The treatment goal is to recycle wastewater and produce water that can be reusable. This is the conventional wastewater flow at Central Park. And by diverting urine, you remove a major part of nitrogen and phosphorus. And by doing this, my previous studies have shown that it can have several positive effects on the treatment plant, which have been reported in my previous publications. However, these studies did not include the energy and process design requirement for the urine treatment, and I'll be focusing on this aspect in this presentation. An approach that our group has been working thoroughly for urine treatment is the biological nitrification process, which removes organics, reduces the pH of your urine, and also converts ammonia to nitrate. This process produces nitrified urine, which could be used as a fertilizer. My goal was to investigate a full-scale nitrification system and understand the energy and process requirements, optimize the DO set point, and also quantify the greenhouse gas emissions produced from a full-scale system. We used BioWin software for our investigation. A lab scale MBR was operated for about 140 days. We configured this process and used this to calibrate and validate the nitrification model to account for the high ammonia and salinity of urine. The calibrated and validated model was upscaled to estimate these parameters for a full scale urine treatment system. When we compare our simulation results with real data from the lab scale operation, it is within the 20% error range value. Hence, this model was further upscaled. These are our full-scale model predictions. So the optimized DO was found to be at 3 milligram per liter without affecting the nitrification rate, which had an energy demand of 3 kilowatt hour per kilogram nitrogen. Below the DO of 3 milligram per liter, the nitrification rate was impacted. And at this optimized DO of 3 milligram per liter, the GHGs emissions were estimated to be at 8.5 kilogram CO2 equivalent per kilogram of influent nitrogen. From our investigation based on full-scale urine nitrification system, we performed a full life cycle and techno-economic analysis. The approach was to compare the operations phase of source separation of urine and processing methods with the conventional wastewater recycling method. We assumed that Central Park had built out urine separation system. The functional unit was 1 kilogram of nitrogen, and we used most of the analysis by Australian Life Cycle Inventory or EcoInvent, and these were our target parameters. So far, we have only completed cumulative energy demand and cost analysis. So we compared different scenarios. Scenario A is conventional, where there is no urine separation. And in this system boundary, we have the conventional wastewater treatment process and the conventional fertilizer production process. In scenario B, we have urine diversion followed by nitrification. So in the system boundary, we assume that 90% of urine is separated and processed. Later, it is stabilized by nitrification at source and transported by road to the agriculture farms. In scenario B, we have evaluated various urine transport options. Option 1 is to use the treated urine for on-site fertigation or urban farming within less than 10 kilometers. The other option is to transport treated urine to agricultural crops, which are about 50 to 150 kilometers away from the center park. The life cycle analysis reveals that about 10 to 50% of the cumulative energy demand can be reduced by urine diversion, which is mainly due to the reduction in aeration energy and the avoidance of Haber-Bosch process for fertilizer production. However, these savings can be counterbalanced by the energy required to transport urine fertilizer product to agricultural farms. Hence, the distance of urine fertilizer shipment plays a key role in determining the net energy savings. Our findings in this study also show lesser energy savings in comparison to similar studies in literature, which may be due to the difference in choice of treatment technology for urine treatment. Sensitivity analysis was also performed to understand the robustness of this process. In option where urine can be used on site, the fertilizer price seems to be the most detrimental factor. and in option where it needs to be transported to distances, the flush volume which we use to flush urine seems to be the most detrimental factor. The urine treatment technology, URWAL, is currently at TRL5, which aims to transition to CRI2, which is a commercial trial small scale. Retrofitting cost is a major challenge to reach CRI2. So a potential solution for this is to capture the idea of urine diversion at a planning and design stage of the building projects, and which is the goal of ARC NICE Hub to partner with some of these organizations in Australia which are in the planning and design stage, and potentially implement urine diversion at these buildings. Last but not least, I would like to acknowledge my supervisors, lab members, and lab technical staff for their support, and the organizers of this summit for giving me this wonderful opportunity to talk about my research. Thank you very much for your attention.
Great. What a fascinating look at potential for urine diversion in Australia. And again, if you have questions, you can feel free to add them to the chat and we'll try to get to them at the end of this panel. I'll pass it right along to Lucinda Lee, who will be presenting on the potential role of urine separation in improving nutrient circularity in New York City, for a look at a different context here. And Lucinda is a PhD candidate at the University of Michigan. We saw a nice tour of that facility from her yesterday in the Civil and Environmental Engineering Department. And she works with Dr. Nancy Love and Dr. Krista Wigginton to evaluate the risks and benefits of urine separation to human and environmental health. So Lucinda, if you're ready to go, you can go ahead and share your screen now. Yeah. Lucinda, let me know if you need any help sharing your slides. Maybe if you'd like, we can go to the next presentation and come back to you if that works better. Let's plan on doing that. So our next presentation, Lucinda, you can feel free to private message me if you want to send me something that I can share or something. Our next presentation is from Luis Perez-Mercado and Prithvi Simha, who will be presenting on nutrient stocks, flows, and balances for the Bolivian agri-food system. Can recycling human urine close the nutrient circularity gap? Whichever one of you would like to share your slides, you can go ahead and do that. And then we'll come back to Lucinda afterward.
Okay, I'll do that.
Great, thanks.
Can you hear me now?
Yes, now we can.
Okay. So I hope you can see the presentation correctly and not the presenter view because I'm a mess here. Okay, so well, good afternoon, and thank you for inviting me to share our findings in this topic. And I would like to start by saying that it has been shown that globally 25% of the Haber-Bosch nitrogen and around 25% of the phosphorus that is mined from rocks can be replaced by urine. In countries where fertilizer use is very low, urine could completely replace it. Bolivia is one of such countries. A previous study found that the applied fertilizers cover only between 15 and 30% of the crop requirements in Bolivia. In consequence, the national government is implementing a fertilizer production facility. Now, going back to that previous study, unfortunately, that study failed to incorporate some key aspects, such as calculating the nutrient requirements, but to optimize crop yields, and failed to account the nutrient inputs from crop residues and manure, and also didn't consider the diversity of production systems across the country. So the purpose of our study was to know to what extent human urine can close the nutrient gap in the Bolivian agri-food system. So to answer this, we had these three sub-questions. How large is the actual nutrient gap? But considering all the inputs, the optimized crop yields, and the different agri-food systems in the country. Other question was, what is the amount of nutrients available in human urine? And finally, where are located the largest nutrient gaps and nutrient sources in Bolivia? So to achieve that, we basically performed a mass balances for nitrogen and phosphorus based on the system that you can see, and with data from the database of FAOSTAT for the year 2018, and data from the National Agricultural Census of Bolivia. We calculated the nutrients in urine based on a previous study by Johnson and Vineras, and we applied these methods both to national and regional level. So about the regions, instead of considering the 9 administrative regions of Bolivia, we considered 7 agroecological zones. This type of zones group the territory based on a landscape, the climate, and focuses on the management systems of crops. The 7 agroecological zones of Bolivia are 4 zones at altitude lower than 1,000 meters and decreasing humidity from north to south, 2 transition zones with altitude between 1,000 and 3,700 meters and decreasing humidity from north to south as well, and a zone with altitude above 3,700 meters. So here are the results. As the results follow the same pattern for both nutrients, for nitrogen and phosphorus, we show only the results for nitrogen. About the posed questions, the nitrogen deficit at the country level is of around 100,000 tons, and the amount in urine is around 35,000 tons. Although the nitrogen in urine is more than enough to replace all the synthetic fertilizer applied, it's clearly not enough to fill the nitrogen gap that we have at the national level. Now, looking at the regional level, we can see that the region 3 has the largest nitrogen requirement, which is around 200,000 tons. And this is more than half of the country requirement. And that region also has a deficit of around 90,000 tons. As at national level, the urine nitrogen would not significantly contribute to closing the gap in this region. A similar trend is observed in regions 4 and 5, although at a much smaller scale. In these regions with large deficits, crops oriented to export and animal production, like soybean and sorghum, are cultivated at a very large scale. To visualize the influence of this production, we simulated what would happen if only 30% of soybean and sorghum were cultivated in region 3. And we can see how much the nutrient gap has been reduced at national level and in region 3. Now, if we consider that the government recently has announced the production of synthetic fertilizers to fill the gap of nutrients for agriculture, we can conclude from this that most of these nutrients will end up abroad. Now, in contrast, regions 6 and 7 have nitrogen surpluses in spite of the large proportion of losses. So These two regions are potential donors of fertilizers to other regions in the country. If the nitrogen from urine was used in agriculture, the amounts of these donations to other regions could increase. About the agricultural systems in these two regions, they are strongly influenced by traditional practices. And the majority of production is for local consumption. Our results showed that most of this nitrogen comes from manure. At this point, an additional question came to our minds. Why the crop yields are low in these regions if there are nutrient surpluses? A likely answer is the geographical distribution of the manure. Although the manure amount is enough in these two regions, the availability is not uniform, as we can see in this map. This suggests that there are zones also with excessive nutrient addition within both regions. And this would apply as well to nutrients from excreta if they would be used for agriculture, because the distribution is not uniform either. So about the research questions, we determined that the nutrient gaps are with 100,000 of tons for nitrogen and 50,000 tons for phosphorus. And we also found that the urine alone cannot fill the nutrient gap in this current system. And finally, we found that the largest gaps are in the regions where animal feeding and export crops are produced. So this gap is caused to a large extent by exportation of nutrients and by nutrient losses during animal production. Finally, the largest sources are in the regions where traditional practices are still applied and production is mostly for local markets. These regions can donate these nutrient surpluses to other regions with support from URINE. If you like to have more details about our study, you are welcome to read the full paper published in Frontiers, or you can get in touch with us. Thank you.
Excellent. Thank you so much for that fascinating look at the case of urine fertilization in Bolivia. And now we'll try to pass it back to Lucinda to do her presentation on urine reclamation in New York City and what that would look like. So Lucinda, if you can try again, hopefully your Zoom will cooperate for you now. And Luis,
I'm actually having a lot of issues with Zoom on my laptop. I sent you my slides, Julia. Is there any way you could present them for me? Okay. Every time I try to use Zoom on my laptop, it's just freezing up.
Alas, I will try to pull them up. Just give me a second here. Let's see. All right. Let's see if this will work. I'll try. So if I kind of can go through them and then you can present from your end, that would be good.
Yeah, thank you. I'm so sorry for all the technical difficulties. I'm not sure what's
no worries.
Actually, I'm going to try it one more time because
okay.
It will respond.
Oops, don't want to open FaceTime. All right, here we go. I think oh, maybe you've got them before I get there.
Is it responding now?
Yeah, we're seeing it.
Great, okay. Okay, and can you hear me?
Yes.
All right, okay, great, okay, here we go. Well, there we go. Okay, so you're all seeing everything, hearing me all right now?
Yeah,
okay,
it looks great.
Okay, sorry about that. Okay, thank you so much, Julia, and everyone for the patience. Thank you for Richard for the opportunity to share this project with everyone here. And this work was really done in collaboration with the New York City Department of Environmental Protection and our team at the University of Michigan. And today I'll share our research approach and the progress we have made so far. I'm really unfortunate. It's unfortunate we had the technical difficulties because we don't have any significant results to share yet. So it would have been really great to kind of tee up, Fernando, your presentation, which had similar research objectives. Right. Well, looks like we're freezing up. Oh man.
I can try sharing mine if you want me to go back to that. Maybe I'll just give that a shot and see if that'll be better here. Is that kind of working?
Oops. Okay, that should be okay. You might have to, I'm so sorry, you might have to download this because there are going to be animations that I'll walk through.
I'm not sure I can quite do that. So maybe I'll pass it back to you for you to try sharing again. If you don't mind trying again.
I don't know what's going on with my laptop. It's just not having a good day. Okay, I think we're back here.
Yeah, great.
All right. Okay, yeah. So I wanted to give a little introduction about the context of urine separation in large metropolitan areas and urban areas, and the idea that urine separation can have potential benefits at the system scale. So particularly there may be potential benefits in improving nutrient circularity, which is this concept of minimizing nutrient inputs from and outputs to the environment by recovering nutrients from waste and returning nutrients to where they are needed. And nutrient circularity opportunities can both be internal to the city or external to the regions outside of the city. Urine separation can also improve centralized wastewater treatments by reducing nitrogen in the wastewater influent, and that can effectively reduce chemical and energy needs of biological nitrogen removal at the wastewater resource recovery facilities, which I may refer to as WRRFs throughout this presentation. And so we all know that New York City is the most populous city in the US. We know it's a really big city. And so as population is expected to increase in the city, there are concerns about increasing nutrient loads to wastewater facilities, at the same time trying to meet increasingly stringent standards for nutrient removal. And so we can think about urine separation as a strategy that can relieve some of the burden on the wastewater facilities, potentially helping the city's Department of Environmental Protection save as much as $9 million every year in chemical inputs. So if we were to think about urine separation implemented in New York City, one of the first questions we have to address is how much urine needs to be separated and processed into a fertilizer to have the desired benefits to wastewater treatment, as well as nutrient circularity in the city. So ultimately, this question leads us to our research objective, which is to evaluate the potential for urine separation to improve nutrient circularity. And our research approach is first to do a spatial analysis of major nitrogen and phosphorus flows throughout the city, then evaluate the impacts of different levels of urine separation on biological nitrogen removal, BNR, at each of the wastewater resource recovery facilities. Then coupling these analyses, we can determine the potential locations where urine separation can be implemented, as well as the optimal levels of urine separation for wastewater treatment processes. So in this first step of our research project, we are using a material flow analysis to quantify nutrient flows into, out of, and within the city. A material flow analysis, or MFA, is a mass balance approach that assumes everything going into a system can be accounted for as internal flows and output flows. And this method enables a mathematic representation of urban nutrient flows, which can be the foundation of further analyses and modeling of these systems. And using this framework, this project characterizes nutrient flows in New York City, both at the citywide scale, but also at community district levels. And there are 59 community districts in New York City. And this will help us get a better picture of where nutrient needs are and where nutrient rich waste is being generated. So we'll be using nitrogen and phosphorus as the materials that we're tracking, but we'll also be tracking energy and water inputs of these flows. And the subsystems for nutrients include the food, waste, urban agriculture, landscaping, and atmospheric systems. We're also doing a flow analysis of water to track urine flows and also to couple water usage with nutrient use. Then the internal flows will be quantified between these systems of nutrients and water, and then the associated water and energy consumption and greenhouse gas emissions of these systems will be quantified. And to circle back to a research question on the impacts of urine separation on nutrient circularity, we're looking at different levels of urine separation and including that in our material flow analysis. So first we have to think about these flows with the system boundary. And in our case, it will either be the city, the full city boundaries, or the boundaries of each district. Almost all of the nitrogen and phosphorus entering most cities can be accounted for in the form of food and fertilizers. Fertilizers are used in landscaping and urban agriculture, but its waste and products will eventually enter either the food subsystem or become solid waste. And food are sold at point of sale outlets to be consumed either in residences or in retail, so restaurants, cafes, bodegas, etc. And then that can become either solid waste in the form of organic or food waste, or wastewater after we've consumed it and it enters in our excreta. And a majority of the nutrients exit cities as landfilled solid waste or gases from biological nitrogen removal from wastewater, as well as in wastewater discharge. We then looked at the impacts of urine separation on biological nitrogen removal at each of the WRRF. And our approach to this is to take a sort of black box mass balance approach to account for nutrient flows at each facility. So the inputs include the influence and any incoming sludge flows to specific facilities in the city that process that sludge. And the major outputs are nitrous oxide or nitrogen gas emissions from denitrification during biological nitrogen removal, any remaining nitrogen and phosphorus in discharge, and sludge that is sent to potentially a dewatering facility, which is just another facility in the city. Or if the facility is a dewatering plant, then sludge cake is what will be processed at the facility and is an output. And urine separation reduces the nitrogen and phosphorus in the influent, effectively reducing energy, costs, greenhouse gas emissions associated with the biological nitrogen removal processes. And in particular, there's an expected reduction in aeration demand, alkalinity needs, sludge produced, and supplemental carbon needed. So really these are associated with this energy costs and greenhouse gas emissions associated with wastewater treatments. So when we come back to this mass balance of nutrient flows at the wastewater treatment plants, we expect to see a reduction of nitrogen inputs at the plants, which results in a reduction of outputs from these other sources of output flows. And so using this approach, we'll assess the cost and energy benefits of urine separation at different levels of separation at each of the facilities. Finally, we can couple these analyses to determine potential locations where urine separation can be implemented and what the optimal levels of urine separation would be at each facility. To do this, we'll use GIS to map net nutrient flows in each of the 59 districts in New York, helping us to identify areas where nutrient inputs are high in the city as potential areas for local return of recovered nutrients from urine separation. And this spatial analysis of nutrient flows and the potential for nutrient circularity at the district level can be coupled with the impacts of urine separation on each of the WRRF to identify areas within the city where urine separation can relieve nitrogen loading on the WRRF of that sewer shed. It can also help us identify areas where we can offset nutrient inputs in the form of fertilizer use. And then finally, we can look at the potential of offsetting nutrient inputs also external to the city, so any regional use of fertilizers, and determine the potential for nutrient circularity using different scenarios of urine separation. So different locations, but also different levels. And with this, our project can lead to similar results as those from a study that was done in Paris that concluded that there's a high circularization potential in the city, especially when incorporating urine separation into their nutrient management efforts. And the results of this study can help us identify locations where it would be most beneficial to implement urine separation and set a foundation for future studies to consider this technology in New York City. And with that, I'd like to thank everyone who's involved, especially our collaboration with the New York City Department of Environmental Protection, our research groups at U of M, different public agencies in New York, and then our infused partners like Rich Earth Institute and NSF for funding this project. Thanks.
Lovely. Thank you so much, Lucinda. Such a fascinating look at the flows going through New York City and the impact urine could have. Our final presentation for this panel is from Jennifer McConville. And as a reminder, after that, we'll have a brief time for discussion, and then we'll have a little presentation of our Golden Funnel Award. So definitely stay tuned for that. And then we'll have a short screen break before our breakout sessions. And in here, we'll be doing the Golden Ribbon Commission discussion and US regulation. And in a separate Zoom, we'll be doing home gardening. And also as a reminder, we'll have recordings of all the presentations available on our summit website afterward. So Jennifer is an associate professor at the Swedish University of Agricultural Sciences, and her work focuses on planning and decision-making for sustainable sanitation with an emphasis on on resource recovery. So thank you, Jennifer, and take it away.
Thanks. I hope everyone can see my slides and hear me all right?
Yeah, looks great.
Yeah. Great, thanks. I'm going to be presenting today some work that we've been doing on trying to there's 3 sort of short studies that I'm going to go through, work that we've been looking at, nutrient quality, retailers' perspectives, and the accessibility of knowledge within the sector. This is part of a project that we call End of Wastewater. And Robin Harder is actually the main PI on this project. So I'm presenting on behalf of him, and Genevieve Metzen at Linköping University, Biljana Makari at Stockholm Environment Institute, Solveig Johannesdotter and Erik Scharman at the Research Institutes of Sweden. So I know many people in this audience already understand the need for circular thinking with regards to nutrients. And I just like to put it in another perspective that we have as well, that a colleague of mine recently did a study here at SLU looking about sustainable diets, have less waste, eating less meat, and doing more recycling. And one of the interesting things that we see in that study, if we look at the current situation in Sweden, is that we have we supply more nutrients to our agriculture right now than we need to. So there's an overabundance of fertilizers that get put back there. But if we were to do this switch to a more Sweden self-sustainability, eating less meat, importing less, this surplus that we have is because we import a lot of food, and that ends up in our manure or feed from animals. But in the self-sufficiency study, that we actually don't have enough nutrients here in Sweden, that because we're importing less. But at the same time, this black box on the end represents a larger fraction of that. So essentially that the more self-sufficient and the less meat we eat, the more important our resources in wastewater become, which I think is a nice thing to start thinking about. So one thing we're looking at then is like, well, what qualities do these recovered nutrients have to have? And we talked to did a number of focus groups with different actors from both the wastewater sector and the agricultural sector as well. And we asked them to prioritize a list that we had developed from literature and other studies about what are sort of the most important priorities for contamination. And what this group came up with as the absolute most important priority is that there should be no contaminants or minimal impurities in the resources that we recover. There was some debate on whether it should be no contaminants or just minimal contaminants. The thing that's interesting about that, though, is if you look at the results from only the farmers, that of course these impurities are still very important, but they also did having a known content of the fertilizer value there. So how much nitrogen, how much phosphorus is also really important for the farmers, especially if we're talking about using this as a fertilizer. And then the other thing that came out of that, of course, is that, so impurities, nutrients, but also these issues of having a more sustainability, long-term perspective and acceptance, as well as the effective bit of the fertilizer are also really important issues as well. So a quick take-home message from that is that safety is a key priority across all groups, but the farmers need to know the nutrient content. But also this issue that came out that there was a desire for more decision support on making these long-term sustainability decisions, that we need more regulatory support, infrastructure adaptation, and knowledge sharing was really something that came out of it as well. And finally, also this last point that we asked them to try and say, so if these are the things that need to happen, who should be doing it? And it was really difficult for these actors to say who takes responsibility for these infrastructure adaptations that we have, for example, besides the fact that there was a very clear need to engage with the end of this recycling. So we need the farmers, we need the food services to be involved in that. That was kind of the only clear super take home of who should do these things. So based on that a little bit, we decided, well, we should look at the Swedish retailers, though. That's been the food industry has been pointed out as one of these sort of blockages possibly in the acceptance issues here. And so we thought, well, could Swedish retailers be a key actor in this, and what is their acceptance of recycled nutrients from urine or wastewater? So we were also looking at these actors because they're also very few actors and have a very key role as far as that they stock the shelves. A few actors stock the shelves, and that what they put on their shelves will affect what the farmers and the consumers can buy or sell. So we went out and we did a study and we surveyed 127 food retailers and asked them how they felt about 3 different fertilizers. We were looking at dried urine, phosphorus that was extracted from sewage ash, and struvite recovered from wastewater. And all 3 of these techniques are being used today in Sweden, so they were relevant to ask. And what was interesting that we came out, if you look at the top of this bar here, that this piece about whether people thought it was harmful to the environment or to their health, and the brown here is that people disagreed with that to a much larger extent. So that not everyone, but there was a majority of people agreeing on all 3 of these, that they didn't think any of these products would be harmful to their health or to the environment. The other key piece that we can point out from these results also is that there tends to be more acceptance of these products, but also particularly more acceptance when it was further away from use as edible plants for human consumption. So there's a decreasing trend here. It's more acceptable for inedible plants, and this trend of decreasing acceptance down to people eating it is evident actually for all of them. But there was also a clear preference for struvite. We were wondering a little bit if the fact that we called it dried urine or dehydrated urine also affected the acceptance level, that the other ones sound a bit more chemical and more safe somehow, would be something to think about, or just there's a preference for more processed types of recycling. So quick messages from that was that there is generally no negative attitude towards reuse in general. But when we also reviewed their strategies, most of these stores also have some sort of sustainability strategies, that there wasn't any clear connection to nutrient recycling within their sustainability strategies. So there is perhaps an opportunity to lobby for. But there is also a perceived risk, which seems to be central to their acceptance. So that we need to also address that this make it clear that what are the risks and how can they be managed. And we also discovered, actually, there was quite a few people that declined to fill in our survey and responded to us that they didn't feel like they had enough knowledge to actually answer this type of survey. So we had this, again, lack of knowledge from the retailers as well as the focus groups that we worked on, which led in some ways, plus evidence that we've seen in other studies and research that we've done, is that there seems to be a clear need in the sector for more information and knowledge sharing about how we do this resource recovery and where can we get it from. So we developed a project to map the evidence on that, to determine what's out there, and we're in the process of developing a database that looks at nutrient recovery and reuse from human excreta and domestic wastewater. We've been working on a co-design process of that, so getting people to tell us what type of information they want in there and how it should look like. What we've done so far is that we've developed a methodology we've had a number of stakeholder inputs within that to come up with this final methodological plan. And we've launched a first version, or 2 versions now, of the database. I'll show you a few glimpses of it. And then we've been trying to populate that database through screening of articles. We've looked at over 10,000 published articles on the topic right now and are in the process of trying to get that in and develop potentially machine learning so that we can continue populating it. Hopefully finally releasing the updated database towards the end of next year, I think. This is what it looks like when you first come in here, that you can see that there's different streams here, urine, feces, sewage, different types of technologies, different types of products that you can get out. So you can search the database through that. It also shows you potential pathways based on the knowledge that's there, the literature that's there. So what urine, what types of treatments is it going through, what types of products are people coming up with? There is a typical publication search as a standard function, much like the Web of Science or Scopus, that we also have a publication heat map, so you can see where the most research is being done, what types of research technologies are most common for a particular source stream. So here, urine, the most common type here is looking at selective crystallization or struvite production. Again, is the most common type of research currently available. We've been mapping that so you can see where the research is being done. So you can look at, you can zoom in on this and see exactly what countries that people are looking for if you want to look for collaborators or knowledge that's out there. And at least from the Swedish context, we've also been creating a Swedish case study database about where these projects are actually being done. Finally, so to finish up, that we have working on a new design, as I said, so trying to complete the database set coming next year, and we're working on how we keep this alive. So how do we open it up for open source editions or machine learning that would automatically populate this? How do we integrate more practical examples, more case studies, even outside of Sweden? And I'm currently working on a pedagogical component. So how can we teach this and both in the classroom, but also for professionals, how we can teach people to actually use this tool. Thank you. That's what I had from me. Feel free to ask questions.
Wow, thank you so much, Jennifer. It's so fascinating to see all those studies from around the world, and definitely, look forward to digging into that database. So we have a few moments for question and answer now. I see one in the chat for Lucinda about whether and how interested the utility is in the results of the study that you presented, Lucinda.
Yeah, I just sent a quick response that this project is we really developed it in collaboration with the utility, which is the New York City Department of Environmental Protection. And I mentioned Samantha McBride, who's in the participant here, who is at this utility and who I've worked really closely with for this project. I don't want to speak on behalf of DEP. From what I understand, though, that there is interest in urine separation in the city, but there is a huge gap, I think, as a lot of the work we're seeing, you know, in terms of infrastructure, policy, perception. So our project is really to get this high level sense of how much urine do we really need to separate and process into fertilizer to have the benefits we desire. And Samantha, feel free to jump in.
Sure. I would say that there's definitely interest, not only on the part of DEP, but also from other agencies and groups in New York City that are involved in sustainable waste management and urban agriculture and farming. One of the big questions is scale, of course, and it's kind of hard to exaggerate the scale that we're talking about in New York City. So from a standpoint of measurable effects at the level of the plant, so reduced nitrogen, reduced energy, increased processing efficiency, there's still very much the question of how many units would need to implement this. From a community perspective, there's a lot of enthusiasm, but one of the questions is, as I raised I think it was the first day, if you go to a building, whether it's going to be built or it is existing, and you say, even if you go with a package of financial incentives and grants to cover capital costs in the beginning, and you say to the building, let's implement this system, at least from where I stand, you have to speak to what the benefits are going to be to the building owner and workers and also the residents. Otherwise, they're not going to adopt it. And that's kind of where I'm most interested right now, is in those kind of questions. But overall, I could tell as soon as I met Lucinda that this is a potentially extremely meaningful project, and I have found to my surprise and delight that others in city government feel the same way.
Thanks, Samantha. Yeah, it's so exciting to hear about these connections being made and the potential for what may be coming in the in the years to come.